Greetings, science fan. We're working more on combined gas laws. We're starting with our first combined gas law worksheet number 1. We already did questions 1 and 2 in the official introductory notes, so if you need help with 1 and 2, go back to that older video that explains what the combined gas law is. Let's jump into number 3. A gas that has a volume of 28 liters. So right off the bat, we know that the initial volume is 28 liters of the gas. The temperature is 45 degrees, so that's the starting temperature. By the way, that's 45 degrees Celsius, so don't forget, you need to convert that to Kelvin. So you want to add 273 to that. Why? Because remember, Kelvin can only have positive values. There's no negatives, so that's why we don't use Celsius in these types of calculations. So that temperature is going to be 318 Kelvin, and it has an unknown pressure, all right? So that means our starting pressure, we don't know. Fair enough. Let's move on. What if the volume is increased to 34 liters? Okay, so now volume 2 went from 28 to 34 liters. The temperature decreased to 35 degrees, so now it's 10 degrees cooler, right? So if it went from 45 to 35 degrees Kelvin, 10 degrees cooler, it was 318, so now it's 308. Or if you wanted to do it the long way, you could just take 35 degrees Celsius and add 273 to it. And if I measure the pressure after the change to be 2 atmospheres, so it looks like my final pressure, P2, is going to be 2 atmospheres, ATM. We want to know what the original pressure of the gas is. So that's why we're going to solve for P1. As you know already, the combined gas law is P1 V1 over T1 equals P2 V2 over T2. So let's plug in and solve for that. Gave ourselves some room. Go ahead and solve that. All right, so P1 we don't know, so that stays as a variable. V1 is 28. T1 we figured out was 318 Kelvin. Super important. You won't get the right answer if you don't convert it to Kelvin. P2 we know from the problem is 2 atmospheres. V2 is 34 liters, and T2 is going to be 308 Kelvin because we added 273 to that as well. Well, to solve that, we can just do cross multiplying if that makes you feel better. So that would end up being P1 times 28 times 308 will equal the other cross, which is 318 times 2 times 34. All right, well, let's go ahead and work that out. If we do 28 times 308, we're going to end up with 8,624 for this side. I'll put that in parentheses. And if we take 318 times 2 times 34 on the right side, we end up with 21,624. Now we want to get P1 by itself. So we're going to need to divide both sides by 8,624. Whoops, and I did that as 42 instead of 24. Let me fix that up. Perfect. We know that's going to cancel out, so you'll be left with P1 for just your answer. And then 21,624 divided by 8,624 ends up being about 2.51. Now the question is, what are the units for this pressure? Well, you just have to look for what the other pressure reading was that you knew. Since the original pressure reading that we had for the math problem was atmospheres, ATM, that is what the units will be for our answer. So it ends up being the initial pressure started at 2.5 atmospheres and ended up dropping down to 2 atmospheres. But there you go, using the combined gas law, as long as the moles and the amount of the gas don't change, we can use this correlation in order to predict a missing variable. Let's try one more example, problem number 4. A gas has a temperature of 14 degrees Celsius. So right off the bat, this thing is starting at 14 degrees Celsius, but we know we want to convert that to Kelvin. So we're going to add 273 to that. So that means 287 if I added my 14 right, and I think I did. So now that we have that initial gas also has a volume of 4.5 liters. So its starting volume is 4.5 liters. If the temperature is raised to 29 degrees Celsius, okay. So if the temperature is raised to 29 degrees Celsius, 29 plus 273 to get it into Kelvin. To go ahead and throw that in your calculator if you need to. All right, it ends up being about 302 degrees Kelvin. All right, and the pressure is not changed. Whoa, what is the new volume of the gas? So we want to know what the new volume of the gas is, but it looks like the pressure doesn't change. So P1 and P2 are equal. Wow, all right, so what do we do with that? Well, if the pressure stays constant, let's look at it from a math point of view. P1 V1 over T1 equals P2 V2 over T2. A lot of people think, well, you can't solve this problem. There's not enough information. But remember, if P1 and P2 are equal on both sides, they're going to cancel out. So we literally can leave them out of the problem because they're equal to each other. You don't believe it? Make them the same number, 5 and 5. When you put 5 and 5 here, you'll see that they eventually cancel each other out in the math. So if anything is ever held constant, you can just get rid of that variable. So now we're left with V1 over T1 equals V2 over T2. And we can solve for V2 no problem by just plugging and chugging. So let's do it. Volume 1 is 4.5. Temperature 1 is 287. Volume 2, I have no idea. I'll leave that as a variable. And the temperature 2 is going to be 302. Now that I have that, I can solve however I like. A lot of you seem to like the crisscross method, so we can do that. Let me do that. V2 is going to be equal to 287 equals 4.5 times 302. 4.5 times 302. Sorry, I ran out of room there a little bit. Let's do that. 302 times 4.5 ends up getting you about 1,359 equals V2 times 287. Let's get V2 by itself by dividing both sides by 287. And once I put that in my calculator, 1359 divided by 287, I end up getting about 4.74. 4.74, but the question is what? If I tell you to go to the store, hey, pick me up 4, you'll say 4 of what, right? We have to label things. So the volume, let's take a look at volume, what we originally had. The volume is measured in liters for V1, so it's going to be liters for V2. So that ends up being 4.74 liters. All right, so hopefully this gives you a good idea of how to set up your problems for the combined gas law. But from there, keep checking away at it and let me know if you have any questions. Great job, science fam.